Good morning, everyone. My name is Dmitry Posnov. I'm an associate professor leading the blood flow imaging group at Aarhus University. Today, I'll introduce two resources we offer for ODIN, one for animal models and one for clinical disease-agnostic applications. Both are part of the translational microvascular imaging infrastructure my group has built. I'll start with a preclinical resource, a multimodal optical imaging platform for in vivo microvascular studies in mice. The resource has three parts: imaging equipment, data analysis, and expertise. The imaging systems are based on light scattering and absorption, so they are non-invasive and do not require contrast agent injections. However, they can be combined with one-photon fluorescent microscopy, for example, for calcium imaging. Access to systems comes with a support on data pipeline, from acquisition to registration and segmentation, and finally to biomarker extraction, and with our expertise on the technical side, on animal preparation, and on interpreting the results. The equipment falls in two groups. The microscopy systems work on any exposed organ, for instance, the cerebral cortex, which they were developed for. The retinal systems use a dedicated lens to capture perfusion and microvascular structure in the mouse retina. And among the microscopy systems, we also have a mobile standalone unit that can be installed in a partner lab or in a clean facility rather than only in our own laboratory. So, depending on the project, the imaging can come to the samples or the samples can come to us. The applications we are most interested in joining in sit within cardiovascular, cardiometabolic, and neurovascular research, both for identifying microvascular biomarkers and for drug discovery. Because the microscopy configuration works on any exposed organ, we can test microvascular markers in many tissues, and we can run chronic, repeated studies in cerebral cortex and retina. The partnership we offer is flexible. It can be a jointly supervised team member, scientific or technical, who is trained to run experiments and performs them in my lab. Or if it fits the project better, my group can take full responsibility for the imaging part of the study. Here are the examples of data from different systems. On the retina, visible light optical coherence tomography resolves fine vascular detail and fibers, alongside with retinal perfusion captured with laser spectral contrast imaging. In the brain, we capture one-photon fluorescent microscopy. For example, here it's a bolus tracking of an injected dye, high-speed imaging of microvascular stiffness and pulse waveform performed non-invasively, cortex-wide blood flow imaging, and optical coherence tomography angiography. Together, these give us both structure and function across the microvascular network. These are the systems themselves. On the left is a standalone blood flow system on table. It's compact and easy to move. In the center is a multimodal system combining blood flow, high speed, and fluorescent imaging. On the right are the retinal visible light OCT system and the retinal blood flow and fluorescence imaging systems. The retinal systems, except OCT, are also mobile and can be relocated if needed. As I mentioned, the imaging comes with a data analysis support. Here you can see a blood flow image that's been automatically segmented and split into regions. The pipeline then makes an automated first guess at which segments are arteries and which are veins, shown here in red and blue, which sets up the later vessel-specific analysis steps. This brings me to the second resource, an optical imaging platform for non-invasive microvascular assessment in humans, primarily in the skin. Again, it includes equipment, software, and expert support. It is a disease-agnostic system. It characterizes endothelial function and the coupling between blood flow and oxygenation non-invasively. It can be used in a reactive hyperemia protocol or for testing topically applied drugs. That makes it relevant across cardiovascular and cardiometabolic research and to any condition where a systemic microvascular component is suspected, including neurodegenerative disease. It's designed for high throughput, large volume clinical studies, though it works equally well in smaller ones. As before, the partnership we offer is flexible. We can fully support the analysis and data can be collected at the initiator site or, if needed, by us. This is an example of the pipeline using the first generation system. It images perfusion in the hand to test endothelial and capillary function during post-occlusive reactive hyperemia. The protocol takes about 8 minutes. On the graph, you see average traces, blood flow in black, and oxy and deoxyhemoglobin in red and blue. First, a 3-minute baseline recording is taken. Then 90 seconds of upper arm occlusion follow. Then the hyperemic response on the release. You can see how blood flow stays low and stable during the occlusion while oxyhemoglobin is gradually depleted. And from the release and recovery, we extract the relevant biomarkers and quantify microvascular function. Here is a first-generation system in a clinical environment with an example of blood flow visualization during the test. You can see perfusion in the test arm drop during the occlusion and then rise again afterwards, the reactive hyperemia response we just discussed, captured in a real patient setting. Currently, 2 first-generation systems are installed at Gostrup Hospital and at KU Next as part of large-scale trials. So the technology is well tested. Around 500 subjects scanned so far and 4,000 are planned by 2029. I can't go into the details of those trials here, but we already see a clear diagnostic potential. Subjects with suspected microvascular condition produce responses that significantly differ from healthy controls. As a resource, we offer access to the second-generation system, which has several important improvements and can be moved to a chosen location for the duration of the study. And separately, as an idea rather than a resource, we propose Optima, a third-generation system with continuous hyperspectral imaging, which would recover a range of chromophores, such as mitochondrial activity byproducts, in addition to the oxygenation, making it an extremely powerful, high-throughput clinical diagnostic tool. Thank you for listening, and I'm happy to take any questions.